I once again welcome you to second day of this ICT program on VLSI design. And our first session will be on CAD tools. And in this session, we are going to discuss the following things. First of all, I will give you overview about the CAD tools. Then CAD tools can be divided in three major categories. And these three categories are capture tools, simulation tools, synthesis tools. And after discussing different kind of CAD tools, we are going to conclude our session and then references. So first of all, whenever any researcher or designer want to start some kind of design, and then he should have, as we discussed yesterday, he or she should have design specifications. Based on those design specifications, and these design specifications act as input to the designer or researcher. And along with these design specifications, some design constraints will also be there with the designer that also you have to follow. And these design constraints may be error. You have to design your system that should be maybe it should be with less error. Then you have to meet some speed constraints. You have to achieve some speed in order to compete in the market. Then some kind of platform will be provided to the researcher or designer, so that they have to implement their design on that particular platform. And if your design cannot be implemented on that platform, it means that you have to do some kind of optimization, and you have to reduce the area consumption of your design. So this area consumption is also very important constraint based on the device you are using for design implementation. And power consumption, yes, we discussed yesterday, for portable devices and handheld devices, power is very important factor, and you have to take care of these power consumptions also. So with these kind of inputs in your hand, you can go ahead with your design. And along with these design constraints, very major or important factor is design tool. What kind of design tool you have? What are the features in your design tool? How you can capture your design? How to simulate your design? And then what are the different synthesis tools provided by the vendor? So after having all these design specifications and design constraints, you have to be very careful about the tools available with you. So with these kind of inputs, like you have a design specification, you have some design constraints with you, then you have available CAD tool with you. What is expected from a researcher or designer? A researcher or designer has to design a system based on these specifications, and they have to take care of error. You have to minimize the error, and you have to take care of speed also. You have to enhance the speed. You have to optimize the area and power consumption in order to provide cost effective solution, so that your product should survive in the market. So all these things you have to take care. These kind of inputs will be there with you, and based on these inputs you have to give the output, and that output will be optimal in all sense. For example, it should be optimal in power consumption, in speed, in area consumption. So with this you can say background, we are going to discuss different kind of CAD tools available for you to proceed with your designs. First of all, we are going to discuss with design capture tools. Design capture tools can be divided in two major categories, as I told you yesterday. Design capture tools can be textual kind of capture tools, or they can be graphical kind of capture tools. Texture capture tools are your MATLAB, where you can write your M code, and HDL is also there, where you can write your code in VHDL or Verilog. And graphical kind of capture tools are your Simulink, where you can design your system with the help of basic blocks, and you can make connection between those blocks. And Another example is schematic. With the help of this schematic, you are going to enter your design, whatever you want to make. Now, MATLAB we have already discussed. Based on some design specifications, you are going to write M code, and you are going to simulate it. Or if you are working in Simulink, then you have to create block diagram in the form of model. You have to create your model for that particular system, and then you have to simulate it. And after MATLAB, when you move from MATLAB environment to ISE environment, in that case you should have your code in the form of VHDL and Verilog. So normally we use two type of HDLs, VHD and Verilog, for our design capture. If we use VHD code, then you give or you express your behavior of your design in the form of Boolean expressions. For example, here you can see the example of full adder, where you have to define expression for sum and carry. You have to just justify these expressions. Before that, you have to define inputs and outputs, as I told you yesterday. You have to define the number of bits, how many number of bits you are going to use for your input, and how many number of bits are you are going to use for your output. No doubt, if you are using more number of bits, your design will be accurate, but it is going to consume more resources, and processing time will be more. And in that case, you have to optimize your design. So you have to select the input and output. We normally call it as IO precision. Input number of bits and output number of bits based on your requirement, in order to get the optimized design. And this is example of VHDL or Verilog. And second kind of capturing is schematic design. Schematic design is basically it is a graphical method, as I told you. If you compare graphical method with textural method, you can here you can see that schematic diagram are used, and these are easy to understand. You can easily understand a schematic. And HDL is basically it is difficult to understand, but yes, you can do modification in this textual kind of input. And whenever we are doing any kind of research, then it is always preferable to use HDL, so that you should have more flexibility. You can make changes in your design, you can modify your design, and then you can check your results and you can compare your results. So different type of schematic editors are there. Vendors are making these schematic editors user friendly. They try to make their softwares more easy to use. They provide you different options like zooming, and different kind of views will be there. You can view on full screen, you can zoom in, zoom out. So different kind of facilities can be there in your schematic design, and you can use those facilities for analysis of your complete design. This is the example of schematic design. Here you can see that we have shown two examples. One is based on gates, another one is at transistor level. So as I told you, we can enter our design in the form of gates, and your software, it should support gate level entry, and then your software should be able to simulate gate level designs also. Likewise, if your design available design is in the form of transistors, then you don't have any other option. You have to enter your design in the form of transistors, and then your software should support these kind of input or capturing. And your software should also support simulation at transistor level. So whatever capturing method you are using, your software should provide that method along with simulation at that particular method. Then next is design simulation and verification tools. Design simulation, and as I told you, it can be divided in three different categories. One is circuit level simulation, another one is timing simulation, then we have logic level simulation. So all these simulations, most of the vendors, they provide simulation at these three different levels, and each and every level is important to analyze your design. If we consider the first one, that is spice simulation. Spice simulation is basically simulation at transistor level. We simulate our design by considering different parameters of that are going to you can say affect the performance of the transistor. As we all know that two type of behaviors are there. We normally discuss transistors behavior as ideal behavior of transistor and non-ideal behavior of transistor. Ideal behavior, three standard equations are there, and then non-ideal behavior, there are lots of parameters are included in this non-ideal behavior, like your velocity threshold, your channel length, and then oxide thickness, and then temperature variation. Number of parameters are there in non-ideal characteristics that we can consider. And there are number of vendors like cadence is there, synopsis is there, and mentor graphics is there, and they are providing solutions and best solution in VLSI design. And each and every vendor, they are providing different number of parameters that can be supported by their software. And if we consider the performance of any software, then we always say that if any software is providing or considering more number of non-ideal parameters into consideration before simulation, that software will be accurate, more accurate as compared to others. So you should always look for the software which are more accurate in nature, so that whatever design you are creating, it should be means based on that design, you should be able to fabricate the chip, and that chip can be used in actual environment. So that is possible only if your simulation is accurate and you are considering maximum number of non-ideal characteristics along with ideal characteristics of transistors. So this is one aspect. But this circuit level simulation, as I told you, we simulate our circuit at transistor level, and we are considering number of parameters. So each and every parameter is basically related with some kind of equation, and at the back end of your software, that equation should be processed. So processing of that equation, calculation of that equation, and then you are going to get the simulated result based on those equations. So from here we can see that if we are considering more number of parameters, it means more number of equations we have to calculate behind the software at the back end, and it will take more time for simulation, you can say that. So these kind of simulations are good for accuracy, for actual implementation, but the only drawback of these kind of simulation is they are time consuming. So these type of simulations are time consuming. And here you can see that we are showing you one simulation, and this is a MOS characteristic. And on the right hand side of the window, you can see that we are using number of parameters. Here we can see VTH, threshold voltage is there. Then you can use ion implantation, means how much thickness you want for ion implantation. All those parameters will be there. So these parameters actually default for different foundries. So whenever you work on some paper, they may use some kind of technology. Maybe they may work on 180 nm technology, 90 nm technology, 45 nm technology. Based on these technologies, these parameter values are going to change. So software is having default values, and based whenever you are going to select any technology, these values will be changed. But again, it is in designer's hand. Designer can change these values, and that is the you can say place where you can make your changes, you can contribute, and you can simulate your design based on these changes. So that is always there in our hand or in researcher's hand. But yes, software is going to provide you the default values of each and every parameter. Then there may be different sources of error in circuit level simulation, and these sources of errors are first of all, as I told you, MOS model parameters. In our this slide, some default values will be there for different parameters, number of parameters. And if we take, as I told you, you can change these values, but these values should be calculated before a change. Means randomly you can't change. If these values are chosen incorrectly, then there will be error in your simulation. So it is not always easy to change each and every value. First of all, you have to do some calculation. You have to create some base on the basis of which you can make changes in these different parameters. Second point is inappropriate MOS model. Inappropriate MOS model here means here you can see that at the top of these parameters, three different levels are there: level 1, level 3, and BSIM. So these are three different levels where you can simulate your design, complete design. Level 1, it contains less number of parameters, less number of we can say non-ideal parameters, and level 3 contains more number of non-ideal parameters as compared to level 1. BSIM contains maximum number of parameters for simulation purpose, and so from here you can see that if you are concerned with simulation speed, then always level 1 is better. Level 1 is going to consider less number of parameters, and your simulation will be done in very less time. But if you want more accuracy, you want more accuracy as compared to level 1, then always you have to go for level 3. Level 3 is more accurate as compared to level 1, but it will be slow in speed as compared to level 1. Level 1 will be high in speed, simulation speed, but accuracy will be less. Level 3 will be more accurate, but its simulation speed will be less. Likewise, BSIM4 is the accurate one. It has the maximum accuracy. It is accurate as compared to level 1, as compared to level 3. The only drawback of BSIM4 is basically it takes more simulation time. So selection of these MOS models, if you are just concerned with behavior of your circuit or logic of your circuit, you want to just view the logic or behavior, then you can go for level 1 or level 3. And you are not concerned with accuracy, more accuracy. You just for example, you are creating one XOR gate, you want to view the output based on your two inputs, and that is the logic. As per truth table, you want to compare your result based on truth table, and then in that case level 1 is okay. You can check the behavior of your circuit. But if you want to check the rise time delay, fall time delay, that thing is not possible. So for accuracy of rise time delay, based on your rise time delay and fall time delay, you check the speed of your circuit, and that can be checked with the help of RC delay, and that is possible at level 3, that is BSIM4 level. So at BSIM4 level, we can get each and every analysis of our design, and based on that you can easily simulate your design, and that design can be fabricated in any one of the industries where you can fabricate your ICs. Then Third is inaccuracy in parasitic capacitances and resistances. If we are not considering parasitic capacitances and resistances in our calculation of RC delay, that is rise time delay and fall time delay, then you will never get accurate speed of your circuit. So whenever you need accurate speed of your circuit, you have to consider parasitic capacitances and resistances in occurred in your complete design, and these can be calculated only if your software is providing maximum number of parameters for simulation, and these two are very important. Based on these only you can calculate the rise time and fall time delay of your design accurate. Then timing simulation, and basically it is used to solve simple non-matrix calculations for circuit behavior. The accuracy of such simulators is less than SPICE simulator. Here we never calculate time in the form of RC delay, rise time and fall time delay. It is a kind of unit delay. We just calculate the delay of each and every gate. For example, if we are using AND gate or XOR gate, we assign delay with AND gate, that 2 unit delay will be with AND gate. If there are 10 number of AND gates, then we can calculate it as the delay of the circuit will be 20. Here we are not actually calculating the RC delay, means we are not considering simulation at transistor level. We are just calculating the approximate idea of delay, unit delay, based on the number of gates available. Each and every gate is basically going to give you some kind of delay in unit delay. One maybe inverter can be calculated as 1, and gate XOR gate can be calculated as 2. So based on the number of gates available in the design, you can get this you can say approximation, means approximately how much delay will be there in your design. But for accurate time delay, you have to go for this SPICE simulation at circuit level. Then logic level simulation. As I told you, you have different options. You can capture your design in the form of gates. You can capture your design in the form of transistors. Here you can see that, as I told you, the different gates may be there in your design. Maybe NOT gate may be there, AND gate, OR gate, NAND, NOR. A number of gates may be there in your design, and each and every gate is related with some kind of unit delay. For example, inverter is having unit delay of 1, not and NAND NOR gates, they have unit delay of 2. So you can calculate the number of NOT gates, NAND gates, NOR gates in your design, and based on the number you can calculate the unit time delay of your design. So these type of simulators are fast, but they are not accurate. They can give you just estimated idea about the delay of your design, but they can't give you exact delay and exact rise time and fall time delay. All logic circuits are rarely active in your design at the same time. Logic events may be scheduled on a queue, and it means that circuit is validated. So here we can see that you have to partition your circuit sometimes. Whenever you start functioning of your circuit, you will never get all the components of your circuit active at the same time. Some part of your design will be active at some time, and some part will be active at the other time. For example, let us say you have one complete design, and in that complete design we have 3 partitions: partition 1, partition 2, and partition 3, right? So if actually partition 2 is dependent on partition 1 and partition 3 is dependent on partition 2, right? So in that case, first of all you have to process partition 1, and result of partition 1 will be used by partition 2 for its processing. So once result of partition 1 is available, then partition 2 will take that result and it will start processing of that particular section. And once that section is processed, then result of partition 2, it will be used by partition 3 for its own processing. And once processing of partition 3 is complete, then you will get the output of your complete design. So in this way, you can say that three sections of your design are working at three different times. So you have to schedule, or you have to schedule your design at different times. So that scheduling you can perform with the help of clock. So clocks, or you can say we can use events. Events can be used to schedule different to schedule working out different parts in your design. For example, in first positive clock, partition 1 is going to work. When the working of partition 1 is complete, then in the second positive clock, second part is going to work, and in the third clock, positive edge of the clock, third part is going to work. So in this way, after 3 clocks, you are going to get the output of your design. So your logic can be scheduled, and a queue can be generated, and that different sections of your design can work at different time intervals based on the clock. So in this way you can and your software should be able to provide such kind of simulations. So here you can see that we have shown you one full adder design at gate level. You can see that. So left hand side portion is basically your circuit, full adder circuit, and right hand side portion you can see that the simulation of that circuit. So as I told you, we have different sections for our VLSI design. If we design with schematic, we design at gate level. We are creating full adder at gate level, and here first of all you have to check the behavior of your circuit. So your software should be able to provide simulation at schematic level also. Only then you can check the logic or truth table of full adder. So right hand side is the simulation at schematic part. So it should be there in your software. Only then you can proceed further. Otherwise, without confirming or without simulating it, without checking the behavior of your schematic, there is no point in moving ahead with your design. So first of all, you have to cross check the behavior of your design. Second is your switch level simulation. Your switch level simulation can be where you can use transistor as switches, right? So RSIM is one example of switch level simulator, and here you use CMOS logic. You can be used then where pull up and pull down transistors are used to calculate the. Here you can see that rise and fall times. So this is one example of inverter, and here you can see that we have designed this inverter using transistor as switches. Upper part is your basically PMOS. It is connected with VDD, and lower part is your NMOS. It is connected with ground, and one LED is connected at the output of this circuit to check the function of your complete design. And we are using one switch as input in order to give 0 and 1 logic to your gate. So as you know that PMOS, when you provide low logic to PMOS, PMOS gives us high output, and when we provide high logic to PMOS, then PMOS provide us low logic. So actually PMOS works as inverter. When you are providing input as 0, you are going to get the output as 1, and when you are providing input as 1, you are going to get the output as 0. And likewise NMOS, whenever the input is 0, you will get output 0, and whenever input is 1, you will get output 1. So in this way these two transistors work. So now we are going to check the working of inverter here. When you make the transition of this switch, initially this switch is 0. This switch is 0 means it means that your PMOS will be connected. When input to PMOS is 0, then output will be 1, means PMOS will be connected. So when this input is 0, then your PMOS circuit is connected. Your circuit, this LED is connected with VDD, and it is going to glow, means your output will be on. So when your input is your 0, your output is 1. And this circuit, this NMOS will act as open circuit, and it will not be connected, and PMOS will be connected, and for 0 you will get 1. And when you make a transition on your switch from 0 to 1, right, then in that case, now this PMOS will work as open circuit, and your connection with VDD will be disconnected, and your NMOS will act as now closed circuit. Your now output is connected with ground, and your this output LED will be low. So in this way, you can see that whenever you are providing a 0 to input switch, you are getting 1 at the output, and when we are providing 1 at the input switch, we are getting 0 as the output. So from here you can see that this circuit is working as inverter. This is basically CMOS inverter, where we are using PMOS as, and this logic is known as pull up network, and this is known as pull down network, right? So this behavior can be checked from this simulation result. Here the first waveform is the input to the inverter, and second one is the output to the inverter. Basically we are using now here two inverters, that is why we are getting two outputs. We can just verify the output of first inverter. Here you can see that when your input is going high, at this point output 1 is from first inverter, output is going low, and again when it is going low, your output is high at this point, and once again when it is going high, again your output is going low. So in this way you can check the behavior of your inverter with the help of these waveforms. So this is complete working of this switch level simulation. So your software should be able to take the design in the form of transistors, and you should be able to simulate the design in the form of transistors. And another kind of option can be mixed mode simulation. Mixed mode simulation can be it can be combination of your gate level simulation and switch level simulation, you can say. You can use gates, you can use transistors also in your circuit, and with the help of gates and transistors you can make your design, and then no doubt your software, it should be able to support this kind of design capturing. Only then you will be able to provide this type of capturing, and then simulation should be there in your software. So after this one, now next is design synthesis tools. In design synthesis tools, basically we can discuss here behavioral synthesis, RTL synthesis, logic optimization, structural to layout synthesis, where structural to layout synthesis contains placement and routing also, right? So first is behavioral synthesis is basically, it is the fastest simulation. It is the fastest simulation, and you can check the behavior of your design without considering actual RC delays, without checking parasitic components like resistance and capacitance. You are basically concerned with behavior simulation, and this one is the fastest, but it is not the accurate one. It is used to decide upon assign the resources based on your area and timing requirements, and also sometimes we insert pipeline registers to achieve timing constraints here. This is one example of behavioral simulation where you can see that again this is one. You can see that both are 1, and we are getting this as 0. This is example of XOR gate. We can see that, and here you are providing two different waveforms for input. We are using X and Y as input in this circuit, and we are just checking the output of Z, whether we are getting output similar to you can say XOR logic or not. So we are just checking the behavior of our design. Here we are not considering the RC delay, means it is not at circuit level. RTL synthesis, this we discussed yesterday on also. Here RTL basically RTL synthesis means it converts. You have the option in your design. Either you can input your design in the form of schematic, or you can input your design in the form of VHDL or Verilog code. If you input your design in the form of VHDL and Verilog code, then RTL synthesis is going to take that textual code, and it is going to convert the textual code into its RTL description, right? That code can be in the form of uh, control flow kind of statements. It can be if else statement. Your program can be in that case. So if we just discuss our system can be divided in two major sections that we will discuss in our next session also. You can your system can include either data flow kind of applications, or it can include control kind of applications. So you have to take care of both things. Control kind of applications means you are getting some physical inputs to your design, and based on those physical inputs you have some logic inside the processor, and that logic will be performed, and you are going to control some outputs based on those inputs and your logic. So you are controlling some physical device with the help of some physical inputs. So these type of activities or these type of circuits are known as control kind of circuits. So that is why we normally have two kind of ASIPs. Here ASIP stands for application specific integrated processors. Under ASIP category, basically your complete hardware, it can be divided in four major categories. Your GPP is here, your ASIP is there, ASIC is there, and PLDs. Yesterday we discussed. GPP stands here for general purpose processors, and example of general purpose processor is microprocessor. All right. So microprocessor is also processing your signal in digital form, but microprocessor, you can say that it is flexible in nature. And microprocessor can be used in number of applications. Means you flexible in nature means you can use this processor for number of applications. For example, we are using microprocessors in our PCs, and we are using PCs everywhere these days, in every branch, in computer, electronics, mechanical, civil, and they are using it for their own applications. So we can say that general purpose processors are they are used for number of applications. Then the second one is ASIPs. Under ASIP category, two more processors are there, and those two processors are your microcontrollers and DSPs. If we differentiate these days in our BE as well as in our ME syllabus, we are in most of the curriculum, we will find that we are teaching microprocessor, we are teaching microcontrollers, then we are teaching DSPs also. So all these three processors are basically processing the signal in digital form, in the form of zeros and ones, but still they exist. It means there is some specific need of these processors. So as I told you, microprocessor is general purpose processor, and your microcontroller and DSPs are ASIPs. They are application specific integrated processors. Microcontrollers are used for control kind of applications. Control kind of applications means if you have some kind of means input is coming from some physical device, and based on some logic you have to control the output. For example, your air conditioning system. Air conditioning system is these days based on sensors. You sense the temperature, Based on the temperature, the temperature, you have to make the compressor on or off. So it means that some sensor is there that is sensing the temperature of that particular area or room, and based on that, it is going to give some input to your microcontroller or processor. So there is some logic. You have written some program in the in microcontroller in order to make that compressor on or off. Based on the so we can say that that sensor is basically working as input, physical input to the controller. Sensor is taking the data, capturing the data, taking that data and sending it to the microcontroller. Microcontroller is analyzing that data and performing the code, running the code. Based on your logic, it is going to make that compressor on or off. So here you can see that you are get some physical devices connected, that is sensor as input, and we are taking signal from sensor, and now we are controlling the compressor again, one physical device that is as that acts as output. So you are going to control that output with the help of your logic in micro. So this is one example of microcontroller. Microcontrollers are used for control kind of applications. For these kind of applications, this statement works. We always use for these type of applications, we use control statements. If this thing, let us say if temperature is less than this, then make compressor on off. So these type of statements are used for control kind of applications. And the other thing is your next is DSP, digital signal processors. Digital signal processors basically they are used for data flow kind of applications. Data flow kind of applications means as we all know that DSPs are used for real kind of data. We take the input, or we take the input data or signal, you can say that, we process that signal and we send that signal to the next unit. For example, your mobile phones, you are basically getting the input data, that input signal, and that input signal is combination of wanted signal and unwanted noise or interference. Now what is the purpose of your this complete system? Your purpose of complete system is basically to remove the interference or unwanted noise from the wanted signal. So you are taking the signal, you are processing it, basically you are removing the noise from the signal, and then you are sending it to the next unit. So these kind of applications are data flow kind of applications. You are taking the data, you are processing it, and then you are sending it to the next unit. So DSPs are used for these kind of applications. So you should be very clear about different processors. What is the purpose? Why they are used in different environments? And then comes PLDs. PLDs we already discussed yesterday. PLDs can be your CPLDs or FPGAs. PLDs are used where you need modification or flexibility because they are reprogrammable. If you know that in near future maybe you have to make some changes in your design, then it is always preferable that you should go for PLDs. You can do later modifications in your PLDs. And ASICs are basically application specific integrated circuits or chips. ASICs are used where you want to optimize your circuit in all the sense, and ASICs are used for that particular application only. ASIC developed for one application, it cannot be used for any other application. For example, you are making one mobile phone and you are providing some features, and you have to create that mobile phone in different Hello. Sorry, participants. Actually, there was power failure at our end, so that is why there was disconnection in our studio and your center. So we can go ahead further. So we were discussing the ASICs. ASICs are basically required when you need those chips in bulk. You need thousands, 10,000s of those chips. For example, if you are creating one mobile model, you are not going to create only one mobile model. You are going to create a number of mobiles of that particular model. So in that case, you design ASIC and you optimize your design for your speed, for power, and for area, and you have to make your design cost effective also. So based on this, basically, so we can say that ASIC is used where you have to generate them in bulk, but ASIC created for one application, it cannot be used for any other application. So if you have developed it for that particular mobile model, it will be used for that particular mobile model only. You cannot use it anywhere else. So these four different options are there. You can select any one of those options under means whichever option is convenient to you. You can go ahead with any one of these. So based on this, control kind of statements will be there in your HDL. Here iteration means looping. You can perform loops with the help of iteration. So you can write your code in the form of you can provide while, do, while, loop kind of things. Hierarchy is basically your you can say one complete microprocessor. Under microprocessor you have different sections, or microcontroller you have different sections, then you have subsections, small sections. So you can divide your larger design into small sub sections, and then you can go ahead with your complete design. Here the next point is word widths and bit vectors, bit fields. Word widths are nothing but these are IO precision. Inputs and outputs means how many number of inputs you are going to use for your design, and how many number of outputs you are going to use for your design. That you have to define your in your HDL or Verilog code. Sequential versus parallel means you can go ahead with sequential design, and there is drawback of sequential design of speed, but it will be cost effective. Parallel design will be high in speed, but it is going to consume more area. So it depends upon your requirement. You can go for sequential, or you can go for schematic also, or this one parallel also. Register specification and allocation. we can provide registers at different locations in your complete design in order to store the results, where those results will be used by some other part of your design. So you can provide these registers at different parts. Likewise, you can have arithmetic logics, and then you have comparisons. You can compare two numbers. Different kind of means logics you can use in your VIGL or Verilog. So RTL compiler is basically responsible for converting your text into registers and combination logic. This is one example of RTL logic. Here you can see that you are writing one VIGL code, and then this VIGL code after RTL synthesis will be converted in this block diagram. You can see that this is RTL, register transfer level. Here we can see that it is just like black box, but with clearly defined interfaces. It has X and Y are the two inputs, and we have C and S, that is your carry and sum for half adder. And then under synthesis, in this synthesis part only, you perform logic optimization. And this logic optimization we are going to discuss in detail in our next session. Um, Yesterday also I explained about this logic optimization. This can be divided in two parts. Basically, it is technology independent logic optimization or technology dependent. So in more detail, we are going to discuss it in our next session. So once this logic optimization is done, then your RTL will be converted into set of gates, and you will go inside the circuit, you can say, and you will get one final minimized circuit, as I told you yesterday, final minimized circuit with minimum number of resources along with their net list connection between different components, so that you can reduce the number of resources in your design. You can enhance the speed, and you can reduce the power consumption. So after logic optimization, you perform all these optimizations. Then comes structural to layout synthesis. Structural to layout synthesis is basically now after this logic optimization, you have the required number of gates with you, along with the connection of each and every component with the other component in the design. So that final network is there with you. Now your task is you have to convert this final network into layout, and that thing can be done after your placement and routing. So you perform placement of your design first, and then you route your design. Placement, again, different algorithms are available for placement. Two most commonly used algorithms are used for placement, and these are min cut algorithm and thermal annealing algorithm. These two algorithms are used for optimized placement of your design on silicon or on your CLBs or PLBs. So you can make changes in these algorithms, and you can develop your own for efficient placement. But these are most commonly used algorithms in at present these days, and we can use them for placement. So once your placement is done, so from here you can see that whatever design flow we discussed yesterday, it is actually coming here in all these CAD tools. So how to follow these CAD tools in your complete design? So after placement, you have to select. After placement, the next part is routing. So routing is now once the components are placed, you have to route the components, and you have to make interconnection between different components. And your routers can be channel router, it can be switch box router, it can be maze routers. Again, different algorithms are there for each and every router, and we use these routers for optimizing our routing part. Once your routing placement and routing is optimized, no doubt you can reduce the area consumption, as well as you can reduce the power consumption of your design. Apart from these routers, we have other routers also, like global routers. Global routers are used to route your circuit globally. Means that these routers are going to travel all over your design. And example of these routers are your global clocks, your VCC, ground, because you have to give ground and VCC to your complete design. They are part of global routing. They move in different part of your design. And then global clock you have to provide to each and every section of your circuit. So that is also part of your global routing. Then this placement and basically routing, it is dependent upon the floor planning. If you have PLDs, you have prefabricated CLBs and PLBs in it. If you have any semi-custom ASIC design, again you have prefabricated resources on that semi-custom chip. So we can basically place. Now you have to place your design on these prefabricated resources. So how to place your design on these prefabricated resources, that will depend upon your floor planning option. And how to select the floor planning. Here in this example, you can see that left hand side, it is showing you FPGA. And if you can view here on top side, this is one small cluster of you can say components or resources. And on the right hand side, this is zoomed view of that particular portion, right? So this is one complete architecture of your FPGA, and this is the zoomed view. Here you can see there's in this structure matrix kind of thing. Here you have different you can say you have different blocks in horizontal as well as in vertical directions. So here you can see that we have different number of floors in on your FPGA. So floor planning means, first of all, you have to select one particular floor out of the number of floors available with you. And this floor planning, it depends upon the IO selection. So what inputs and outputs you use in your design. And in VLSI design, we always take care of shortest path. So whenever you route your circuit, you have to find out one route that is shortest possible in order to reduce the wire length, or in order to reduce the interference, in order to reduce the area of your circuit. So it is always applicable in each and every place. So you have to find out shortest path for your routing. So that is why, based on these IOs, you can see that on the top side, these two pins are used for input. On the other side, we are using these two pins for output. And based on this IO selection, we have selected the floor which is closer to these two IOs, inputs and outputs, so that your routing will be shortest possible. So we are first selecting the floor which is almost at equal distance from both the inputs and outputs. So here you can see that we have selected one in between floor. And once this floor is selected, sorry, in that floor also there are number of CLBs or PLBs. You have to select particular CLB for your placement. So again, we are selecting the closest CLB or PLB which is close to the inputs and outputs. So that particular CLB is now selected. So once this floor planning is done and that particular area of placement is selected, then you place your required circuit on that area, in that area. So once that placement is done, then you make interconnection between different now components. So in this way, this floor planning, it plays very important role in placement and routing, right? So all these things are very important. So you place your circuit. Once now once your circuit is placed, the next part is now you have to make final connection between your different components you placed over the CLB or PLB. and on silicon area. So in this area here again, this is the routing part here, left hand side, and here you can see that this is the zoom part where your circuit is placed, and these bright wires are basically routed wires, final routing of your design, right? So you have different options in your softwares. Your software is providing analysis at each and every section. We are designing our circuit in schematic, simulating it. We are now converting it into a layout. It can be converted into a layout, or it can be transferred to PLB, and then again you have to simulate it, and you can internally view where your circuit is placed, what floor is selected, where it is placed, and what are the routing options, where it is routed, how it is routed. So these are different options where you can view your design, you can analyze your circuit. So these options are available with different tools. So finally, these three type of now tools are there for different vendors. So we can conclude our session here depending upon the input with the designer, like circuit, whether circuit is in the form of gates, or is it is in the form of transistors, or it is in the form of code, right? You have to design your circuit, uh, and depending upon the software available with the designer, depending upon different design constraints, you have to fulfill the design constraints in terms of speed of your design, in terms of area consumption, in terms of power consumption. So design can be captured by maximum number of options. So if you have more number of capturing you can say methods, your software is more flexible, and I means you can design more circuits, more you can follow more papers. You may have different papers on various research sites. So you can capture your design. If you can capture your design in number of methods, you have flexible options. Then you have to verify your design by simulating it. Then synthesis option, it should be there, and synthesis should be optimal so that you can get optimized results, and then you can get one optimized design in terms of different parameters like speed, area, and power, and you can come up with one design that is cost effective, that is acceptable by market, and your product can survive in market. So CAD tools play very important role in designing your circuit. So this is all about this exposure of CAD tools. You can have different references related to this session. Neil Veste book is there on CMOS VLSI design. Then you can use user manuals from ISC. You can use user manuals of DSCH and Microwind. And this is all about these means CAD tools. Now we make this session open for different nodal centers, and we are happy to give answer to your queries. So you can now go ahead with your query part.